Hey, welcome back. Today is 2.11 logistic growth functions. Let's take a look at our goals. We have a few. First being describe the effect a given parameter has on a graph. We've seen this in every lesson all unit long. A parameter is just another way of saying transformations. There's something changing when we look at these functions. Different values, graphs are a little different. Evaluate a logistic growth function for a given input value. What does that mean if you take a given input value and you evaluate? Well, that means sub and solve, right? Also, interpret key features of logistic growth function in terms of real-world context. You're going to find out very soon that these types of functions very much so help you figure out things in the real world. And of course, we will be graphing them as well. So let's get into it, starting with this exponential growth graph. You've seen these before. Exponential growth. It starts out very slow and then it skyrockets up. Okay? Now, as we've previously learned, many things in the real world can grow exponentially, like the spread of a virus or a financial investment. Now, do you think these things, think about this in the real world, do you think they typically tend to increase exponentially forever? I know forever is a big word, right? That's a big math word and that's a big real life word. And the answer is often no. Most things that start out growing exponentially don't necessarily continue to do so forever, which is exactly where logistic growth functions come in. Things begin to slow down and eventually reach a limit. We see that graph over here, okay? And when they reach that limit, they don't grow past it. There's a cap, okay? So where do you see that on the graph? Hopefully you're looking at this dashed red line. This is the limit. We see the exponential growth starting, but then things begin to slow down and they don't pass there. They're going to max out wherever that line is. Now, where is that line? We're going to find that out right now with some vocabulary. You see this. But first, let's read a little bit more about it. There was a little glitch there, but we're back. In a logistic growth model, the growth rate is initially similar, it's exponential, when the population is small, right? Resources are plentiful, growth is gradual, it's all good. The population grows exponentially, the rate of growth just gets faster and faster. It's shooting up. But with a logistic growth function, what happens? It reaches a point of maximum growth. We see that labeled on the graph. And that is when resources become limited, depending on the situation. If we're talking about a population, maybe the food in the forest becomes limited, so the population of animals decreases. If we're talking about a virus, they start to get vaccines and cures, so the cases decrease, right? Whatever the case is, that point of max growth is the turning point. Now, I know what you might be thinking. Wait a second, Mr. T, isn't this going up? Technically, yes, but is it going up equally as fast as it was prior to the point of max growth? And visually, at first, maybe kinda, but think about it. Exponential growth continues to go up, skyrocket forever, right? Wouldn't you say this blue line is slowing down? So that's exactly what's happening. The population continues to grow after the point of max growth, but at a slower rate. And eventually the population levels off at the carrying capacity. So this is one of our keywords, carrying capacity. It's at y equals c. We haven't learned what c is yet, but you're about to. And then the other horizontal asymptote you see here is at y equals 0. That will always be because you can't have a negative population, right? Or a negative number of virus infections. Just can't happen. So let's learn about the function itself. Don't worry about writing this down. You're going to see another page with all of the most helpful information come your way very soon. For now, let's just understand it, okay? This is the parent function with all possible changes that can be made, where a, b, and c are positive constants, okay, and x is the only variable. So this is the function we're going to use. Here we see some numbers. So please identify A, B, C, and E. Let's see how you did. A, I see plus A, so that's whatever's in front of E, 4. B is a tricky guy because you see that negative out front? So that acts as dishonest H does, right? Because think about it. If you see negative 2, which you do here, we see negative 2x. What did you have to put in there to see that? Well, 2, right? Because then you'd get negative 2x. So B is not negative, but positive, and C is the numerator, 120. Remember, C also gave us that horizontal asymptote. That is our limit, right? That carrying capacity line at the top. And finally, E. What is that? Well, you might remember E from natural logs. Okay? We don't really care about exactly what number it is, but it is a number often found in nature. Okay, you can use your calculator and find that out. We don't really care that much because we can use our calculator to help us, but you're not always going to need it. And you'll see what I mean when we work this out. Same function, okay? And a little more about this function. It models the population growth of a certain bacteria. So that's what we want to find, the population growth of a certain bacteria. We want to monitor it. We want to track this growth over time, where X represents time. Okay, so where do we start? Well, when you first decide to track the population growth, you want to know how much bacteria you're starting with, right? Because then you can truly track the growth. So given that time equals x, and we're just now starting to track the growth, what can we do with this function to find this information? Specifically to find how much bacteria we have initially. Well, if no time has passed and x is time, which it is, then we're plugging in 0 for x and we're working this out. Now, you could use your calculator here, but I'm not going to because I want to remind you of something very important. Negative 2 times 0. Okay, so numerator is just going to stay the same for a little while. But what happens down here? I see this, and then I see negative 2 times 0, that's 0. Interesting. What do I do with this? E to the power of 0. This is what I wanted to remind you of in case you forgot. What is e to the power of 0? Hopefully you remember that anything at all to the power of 0 is 1. So we get 120 over 5. So finally, we found out that f of 0 is 24. What does this mean, though? It's important that you understand that. Well, it means when zero time has passed, when we started observing this bacteria, there were 24 bacterias. Okay, we don't know what kind of bacteria, they didn't tell us, but we're on our way to learning more about how it's growing. And if you wanted to find out over time, you could plug in one or two or three. They didn't give us increments like months, weeks, days, but you get the idea. You can track the growth over time by putting in the different variables of time. And this is the single most important page to help you answer all the questions you will need to in this lesson. And if you see questions related to logistic growth function at any other time, let's make sure we understand what we see. The graph of a logistic growth function has the following features. Horizontal asymptote at y equals 0. Remember, that is always true because you can't have negative populations. You can't have negative um, bacterias. Okay? And then y equals c. Where is c? Well, that is in the numerator. So that is our other horizontal asymptote. That's also called our carrying capacity. Point of maximum growth. Remember, that is that point right in the middle. How do you find it? Using this. We already talked about A, B, and C, right? For those, you just look at your function. But what about ln? What is that ln? Like, for example, let's just say A was 4. What do we do with that? Well, you plug it in your calculator. That's it. Don't worry about the ln too much. And the y-intercept can be found by this. That's interesting. That kind of looks like this. Well, you're right, and here's why. Based off what we did just a moment ago, we found out that when anytime we have a y-intercept, x is 0, we already know that. If we plug in 0, we have e to the power of 0, which is just 1. So can't we just save ourselves some time and energy and get rid of that to find the y-intercept if it's always going to multiply by 1? Exactly. So you just use this, plug in C and A, and you're on your way to find that y-intercept. And this is a handout in the recordings document. And now it's time to put these tools in our tool belt to use. We're being asked to graph this function. We're told it models the number of people infected by a fast spreading virus at time X measured in weeks. How nice. This time they tell us the actual time increment. That makes this more interesting. So, horizontal asymptotes, y-intercept, point of max growth, other points. Pause this, see if you can use the information below to help you do this correctly. Horizontal asymptotes, we said there's always one at y equals 0 and at C. So if C is the numerator, 200,000, then y is the horizontal line at 20,000. What do we do next? Y-intercept. Use the formula below. C over 1 plus A. C is the numerator, 20,000. 1 plus A is 199, so we have 20 big ones over 200. What's that? Well, that is 100. So when x is 0, y is 100. There's our y-intercept. Point of max growth. That was another formula we saw. We see it below here, so let's write it out and fill some things in. We have two fractions. We have some pretty large numbers, so let's make it nice and big. We know we have ln here and we have 2 over there. So what is A? A is the 199 next to the E. Below that, we have B. B is in the exponent. And remember, that's a tricky guy. If you see minus, it's actually positive. Sonus H is rubbing up off on him. Okay, and then we got what? We have C in the numerator. So that goes right there. And when you simplify this using your calculator, you'll get 10.59 and 10,000. So this graph, we're not going to draw the biggest graph in the world. We're going to use the right value increments to draw a small graph that fits these large numbers. And how can we find 2 more points? Just like any function, pick an x value and plug it in, right? We're not going to do that because you can do that and use a calculator if needed. But we're now going to look at the graph. Okay, what we just found together was this point of max growth. We also found this y-intercept down there. And we found this asymptote and that asymptote. So what we didn't find together is a point here and there. But if you're graphing this and you have a y-intercept and that point, you'll know, okay, I need to pick one x value between these. Could be any of these x values to get a point somewhere in here. And then an x value anywhere a little bit after the point of max growth to give you a point somewhere up here. Okay, there is our graph. Now we have all the tools in our tool belt and we have some practice. So now is a good time to pause this and test yourself. Can you find f of 0 and f of 1? Sub and solve. Just like we saw in our goals, right? Okay, f of 0. I'm just kind of ignoring the numerator for now. If you want to write it every time, do it. But I know I basically all need to do all my work in the denominator, and then I can bring in that numerator later. Okay, so that's exactly what I do. I plug in 0. I know that's going to be e to the 0, which is just 1. So for this one, if you wanted to maybe instead use your y-intercept formula that we saw right here, you could totally do that instead. Save yourself some writing. Okay? But you get e to the 0, which is 1. So you get 1 plus 9, 10, 2,000 over 10, 200. So that's f of 0. And then f of 1, plugging in 1. Now this time, you're not going to get that 1 right there. So you will need a calculator. Okay? A bit of advice, if you're using a handheld calculator, you need to put the entire denominator in parentheses. If you're using a Desmos calculator, it will look exactly the same. So just visually check. Okay? So this time when you plug in 1, you get -4. E to the -4, well, I went ahead and did that, worked that out on my calculator. If you wanted to instead, you could plug in this entire function with that 1 in there, and as long as you typed it in correctly, you'll get the right answer. But I just went ahead and then multiplied that, added those, following our order of operations, and then bring that numerator back. If you feel like you'll forget the numerator, then leave it. Don't take it away. Okay, we just have a little more practice. Several questions here. Use the graph. to identify the listed features of the graph. Okay, horizontal asymptote. So if you want to test yourself, pause this. If you need a little more practice, then just follow along with me. Horizontal asymptotes. We know they are at y equals 0 always. And what do we have? We see y equals that carrying capacity at the top is at 12. Y-intercept. Use the formula from before, right? C over 1 plus A. C is 12. A is, do we know what A is? No, but we can see it on the graph. So this time we're using a graph more so to help us answer these. That is right there, right? Y-intercept. So that's at 0, 3. C, the point of max growth. Well, we know the point of max growth is exactly halfway. We could just take the carrying capacity, this 12, and divide it by 2. It's kind of like a midline, but it's not a line, it's a point. So, but it's halfway between. So all we need to do is take 12 divided by 2, and we get 6. So the point of max growth, um, we have 6, but do we have the x value? Because that tells us how high, right? So let's look for a point. Do we see a point with a y value of 6? We do. So excellent. We were able to identify that. You can't just guess. We had to actually do a little math there to be sure. But now we know the entire point of max growth is right here. D, where the growth rate is increasing. So this is a domain. You are listing this just as a domain. So where is it increasing? Okay, well, we went over this, right? We said this entire way, all the way up until the point of max growth is increasing. So we could say from negative infinity, because remember, this horizontal asymptote at the bottom at y equals 0 means our graph line will never touch or cross it. And it goes all the way right until the x value of what? 1.57. Is that point included? Absolutely. But actually, it's an interesting point. It's actually a neutral point because it's the exact moment where you transition from growth to decline. So it's actually going to be a parenthesis. And then, of course, growth will just continue from, or decline, sorry, decreasing, will continue from there on in the positive direction forever. Show that with a quick highlighter. Decline as soon as you hit that point of max growth. Everything after that is going to go down, or slow down, I should say. Okay. Let's look at another one answering the same questions. This is good practice. We're now getting into some repetitive practice to really help you get comfortable with these. Once again, test yourself. Let's see how you did. Horizontal asymptotes. Okay, remember it's always y equals 0, and then y equals whatever c is. C is the numerator, in this case 15. Y-intercept formula. Here we do see A and C. A is 2, C is 15. Boom, boom. Add, divide. Y-intercept is at 5. C, determine the point of max growth. Again, that formula, we see it below. So we need to identify A, B, and C. Be careful with B. I see minus 0.9. So B is positive 0.9. Okay, for this you'll need a calculator. You'll find it to be 0.77. Here you could use a calculator, don't really need to, but you get 7.5. And again, we're being asked, where is it increasing and where is it decreasing? Well, we know for all of these graphs, they kind of look like an S or a snake, right? So we know up until the point of max growth, once again, it goes from negative infinity up to whatever that x value is. So what is that x value? Well, we found it right here, right? Point of max growth, 0.77. So there it is. And again, decline will be after that. So from 0.77 to the right forever. This is just a little visual of what we wrote, what we answered for D and E. Well, hopefully you're understanding this better. Now is a great time to do one final check to see if you are. This is your exit ticket. Read the question through and practice. Test yourself. Okay, so you were asked first, how many people were infected when the outbreak began? We did a problem just like this, right? Where no time has passed. When it very begun, time is the variable, in this case, t. Okay? They told you t weeks. T weeks. And no, for these functions, the variable is always the time. Okay? Because you want to find out how much growth happened after this much time. Okay? So we plug in 0. Okay? And again, you get that e to the 0, you get that notorious 1, add, divide, you find out there were actually 60 people infected when the outbreak began. Okay, well, just like COVID and other viruses, we want to find out how fast is this growing? And when is it going to stop growing? Right? That's really important. And that's exactly what we're being asked. Over what period of time was the rate, um, over what period of time was the rate at which people became infected increasing? So that visualize it up to the point of max growth, right? So we really need to find the point of max growth. So once again, use that formula right there, plug in ABC, a little calculator work, and you'll find out that this was the amount of time. Remember, X, or in this case, T, is time. Okay? So rounding that up to roughly 2.8 weeks. Okay? Not the best, not the worst, but now we've helped crack this case. With that said, we are done learning about logistic growth functions, at least for now.